Everyone, so we are about to this Grothendieck-Teichmüller theory 1-week conference, and I welcome you all. And some of you have taken a lot of non-trivial effort to come here. Sometime arriving at 4 a.m. morning and sleeping just before this. And so, before we start, I would like to first of all thank ICTS for making it possible to come all of us together and for this meeting, and especially Mr. Raju, who has been very helpful to us, and Mrs. Aruna in the program office team, and some expert member in the program office who initially reviewed our proposal and finalized it in a very timely manner. And so with that, I would like to request Professor Manish to introduce a speaker and we start the meeting formally. Thank you again.
Okay, welcome to the first session of Grothendieck-Teichmüller theory workshop. And I'm happy to introduce Pierre Lochak. He's also the organizer, and he'll give 2 talks today in the first session on the history of it. Yeah.
Thanks. Do I speak here?
Or maybe directly from there.
I don't know. Do I need this? No, maybe not. So, well, first of all, I'd like to thank you all to be in this hall and welcome you in Bangalore, although we arrived in yesterday night, so I don't know much about Bangalore. I've not seen very much about Bangalore except this very beautiful institute. And so I would also like to thank Devendra and Raju for the organization. So this is about Grothendieck-Teichmüller theory, and I'll try to give a historical survey, sort of a historical survey of the theory. I apologize to the many experts I can see in the room who will probably know much of what I will be saying, but that's that was the idea. Actually, the idea is also that Grothendieck-Teichmüller theory is, in some sense, not in some sense, it's actually much wider than what is commonly called dessin d'enfant. And I'll try to stress the fact that it covers, or according to its founders, whom I'm going to talk about, it covers actually a much wider range of mathematics. So I'll say, well, I will, on the one hand, I will announce sort of what we'll be talking about in this workshop. There will be 14, I think, lectures on Grothendieck-Teichmüller theory, 2 on abelian geometry, and some other lectures on subjects which the lecturers have chosen. And I'd like also to say that all of you young researchers, even if you don't deem yourself young, you can come at lunchtime and we'll arrange something, because there is room for a few lectures, and that would be great. So let me start with the history of the theory. So there are, you can say there are 4 main sources, I would say. The first is, of course, Grothendieck. So the first is Grothendieck, Esquisse d'un programme. So I write in French, sketch of a program. Esquisse d'un programme. Sorry for my bad writing. I think it's 1984. So probably most of you have read it in French or in English. So what it does introduce dessin d'enfant, what is now called dessin d'enfant. So that was what was striking to Grothendieck is, I'll come to it in a minute, is the fact that the Galois group acts faithfully, and the key word is faithfully, and acts and not representation. So it acts faithfully on the free group on the profinite completion of the free group on 2 generators, and we'll see, of course, much of it, including in the second talk. This was really striking at the time, and you have to contrast it. I mean, one contrast is linear versus nonlinear. So in the Esquisse, it's really a foray into nonlinear mathematics. Grothendieck writes that after he had a break in 1970, as you know, from 1970 to 1980, it didn't do much mathematics, or he didn't think very much about mathematics. And from 1980 to 1990, he produced 3 or 4 very influential manuscripts. And one keyword is nonlinear. So it was not only used, but I mean, it was instrumental in introducing linear representation of the Galois group via étale cohomology or various brands of cohomology. But these representations, of course, were never by far faithful. Whereas here, he finds via Belyi theorem, we'll talk about it this afternoon, I mean, next talk and this afternoon, via Belyi theorem, you find a faithful action, not linear representation of the Galois group. That was the striking point, really. Then in the Esquisse, you have the two-level principle, which is responsible for the very existence of the theory. If there were no two-level principle, there would not be any Grothendieck-Teichmüller theory. And I'll talk about it Thursday. 3 very different views of the two-level principle, very different, one by Hihara, one, then I will sort of vindicate what's in the Grothendieck sketch of a program, which has to do with moduli stacks of curves of any genus. And then I'll talk about complexes of curves, but that will be, let's say, on Thursday. It's Thursday, Friday. So there are at least 2 ideas. One is this faithfulness of a Galois action on something which is basically comes from topology. I'll talk more about it later. And the other one is the two-level principle in a very general, it's a very general view of the two-level principle, much more general than what is usually done. And I'll talk about it on Thursday. There are a few others, well, there are some other interesting, of course. Well, no, maybe right now I'll say again, not again, but what are we talking about? We're talking about the fundamental group. So the very, very first observation is that the fundamental group, pi1, is the only a priori non-abelian invariant in classical algebraic topology. So this observation, somebody would not be Grothendieck, just an ordinary mathematician would say, yes, okay, would just nod and say, yes, it's true. Homology and cohomology are just linear things, and the higher pi1s are abelian for a reason which is really elementary and has to do with the little disk operad. So you can the little disk operad can enter the subject. We're not going to talk about it, but it does enter the subject. But anyway, the fundamental group is the only a priori non-abelian invariant in classical algebraic topology. So what do you do with that? So here I'll say I'll write it in a slightly technical. I mean, just in a normal way, and then we'll talk about it. So there's a faithful representation. There is the two-level principle, and even more sort of fundamental is the fact that almost everything we'll be talking about is about the fundamental group. So why is it both a very elementary observation and also very important? One contrast is with the rational homotopy. Rational homotopy theory is about precisely not the fundamental group. So rational homotopy theory is about what Sullivan calls formality, which is reconstructing the homotopy type and even more of a manifold using only the, say, the algebra of differential forms in the good cases. And usually people start by assuming that the manifold is simply connected. So there's no fundamental group. At best, you don't assume it's simply connected, but you assume the pi1 is nilpotent. Here, it's the exact opposite. So the exact opposite, what is the exact opposite? It was people called aspherical manifold. So an aspherical manifold is what other people call the KG1 because it's an Eilenberg-MacLane space of type 1. So it's a space which has only the fundamental group. All the other homotopy groups vanish. And the fundamental group can be anything. Let's call it group G. So we're talking about aspherical manifolds. So the moduli space of curves are aspherical stacks, actually. I mean, they're stack K pi ones, or they're rational stack K pi ones. So it's the exact, I mean, it's really in contrast with rational homotopy theory, and it's very important because it says in a way that this is really nonlinear, and I'll say just a little bit after what this entails. So what does, by the way, what do I mean by nonlinear? Nonlinear means non-abelian, but what does abelian mean? Abelian means either abelian or nilpotent or pro-nilpotent or solvable or pro anything. So it's it's beyond pro-solvable groups, say. So nonlinear means beyond pro-solvable. So it doesn't mean, for instance, a successive extension of abelian groups. So, and that produces three. So it produces three theories, one can say. So one is GT theory, what we were talking about. One is the other one is anabelian geometry. And we'll have a glimpse of it in only a short, we'll talk a little bit tomorrow night. And that is, Nakamura will talk a bit about it on Tuesday evening. And Florian Popp will give a survey on Wednesday morning. Anabelian geometry and the section conjecture. So you see, I wanted to say relatively little about Esquisse d'un programme. Now I think I'm saying too much, but that's okay. Let's leave it this way. So the second one. I'll say much less about the other sources, although it doesn't mean that they deserve less, but I'll say less. So the other one, the second one is Yasutaka Hihara. Unfortunately, I don't remember the title of the article. It's Annals of Math, Annals, 1986. So I call it Altes Traum. He used to call it his Altes Traum. So the dream of its, oops. Okay, Kronecker had a Jugendtraum. So the dream of his youth, and Hihara had what he called his Altes Traum, although now I realize that he was not so old at that time at all. But his Altes Traum, that he would say in a very, very broad way, that it had to do with elaborating a non-abelian Hirasawa theory. And Sujata will talk about Hirasawa theory. So I hope we'll hear more about this. What I can say is, maybe I can take this opportunity of saying that you see where we are busy with are braid groups and what we call Teichmüller groups was topologies called mapping class groups. And these two kind of groups, they had been introduced in the early 20th century by Artin, Emil Artin, the father of Mike Artin, and Dean and other people, but then they'd been sort of forgotten, not forgotten, but they'd been left on the side, just like knot theory and everything which had to do with these groups, because people were busy and very, busy in a very intelligent way with, for instance, the cohomology of arithmetic groups. Somebody like Serre, for instance, had never really worked with braid groups or much less mapping class groups. So it was, it was more about, say, arithmetic groups. That is, let's say the schemes, how do you call it, the GL schemes, and all the linear algebraic groups and their cohomologies and so on. So this the revival of the braid groups, which happens here, of course, here, and the mapping class group as an object of study in this kind of framework is by itself very remarkable. The third source is of course Drinfeld's very famous paper. So Drinfeld is 1989. So I don't write the title because it's too long. So it's still Leningrad Math Journal. So it's maybe the most famous paper of the subject. Title is long, then it finishes with and a group closely related to Galois Q-bar over Q, the group being the Grothendieck-Teichmüller group. So this is yet another different trend. So this has, of course, to do with quantum groups. And it has to do with physics. In what way? There was a school, maybe most of you know that there was a famous physics school in Leningrad, headed by Ludwig Faddeev, busy with, among other things, what one calls quantum scattering. And quantum scattering, so you have, things sometimes just thought with pictures. So the picture is just this. So that reminds you of braids. But this is also quantum scattering. Quantum scattering is something which, here you have a Hilbert space. Here you have an initial state. Here you have a final state. Particles do what they like in between. But you pass from the initial state to the final state via a scattering operator, which is an automorphism of or an operator, a linear invertible operator of infinite dimensional Hilbert space. So this is how it all started in a way, but not in a way. I mean, it's really the way Drinfeld got the idea of, the first ideas of this, what was to become a Grothendieck-Teichmüller linear theory and so on. And a very important idea is deformation of associativity. So nobody had ever thought of really investigating the deformation of associativity. Deforming commutativity is sort of both easy and only mediumly interesting. That is, you can't do very much. This is a braid with two, for us, it could be a braid with two strings. So all you have is you can raise your commutativity operator to a certain power, which we will see in Grothendieck-Teichmüller theory. But deforming associativity, you will see that it has many, many translations. And something we won't talk about, and somehow I regret it, is Grothendieck-Teichmüller theory in deformation theory. So there's a brand of Grothendieck-Teichmüller theory which has been introduced in deformation theory, first by Kontsevich, some time ago. I mean, 20 years ago, even more than 20 years ago. And unfortunately, we won't talk about it. We have here a specialist, and there's no lack of experts, but we can't talk about everything. And the last, well, it's not really the last, but the last source I will mention, is the famous another paper by Pierre Deligne, which is in French because he writes only in French. So I just write P1 minus 3 points, but it's actually more complicated than that. I mean, the title. I refrain from saying the full title. And this is MSRI. I don't know, 1990. I mean, it's published in 1990. But what is it that is striking in Deligne's paper is that there's one sentence in the introduction, which is a turning point of the domain. So the sentence says, and it's very unfortunate, very specific. It says, and it's in French, of course, and it says that Deligne, Grothendieck explained to me that it was really important to study the profinite completion of P1 minus 3 points. By the way, I should say that in STA1, which is 1959, there is a problem. There's something which is called a problem, which is called le problème des trois points, the 3-point problem, which is precisely about P1 minus 3 points. So when Grothendieck wrote Esquisse d'un programme, it was recalling first SGA1, which is the only nonlinear SGA, because the SGA1 is about the fundamental group. All the other SGAs can be called quote unquote linear. And it was recalling very old lectures he had given in the Cartan seminar in the late 50s about Teichmüller theory and moduli spaces of curves. Now, Deligne comes and he says, okay, Grothendieck tried to explain to me that it was very important to study the profinite completion of P1 minus 3 points. Unfortunately, I don't know what to do with it. I mean, you really said it basically. It's too complicated, and maybe could have said it's too nonlinear, because the toolbox is completely different from the linear one. Or should have been. I mean, it's completely different here in Grothendieck Esquisse d'un programme. And he says, okay, I don't know what to do with P1 minus 3 points. With the profinite completion, I'll study the pro-unipotent completion. But it may sound technical, but in some sense it's not. It's a complete shift of paradigm, as people would say. It's a total linearization of the theory. Because if you stick to the profinite completion, well, of course, we'll give more, we'll give definitions, or at some point there will be definitions and more, specific and elementary things. But if you stick to, if you really deal with the profinite completions, what Grothendieck was after was something which is much vaster. So first, he wanted to deal with all the moduli spaces of curves, and not only in genus 1 and 2, in genus 0 and 1, but also he wanted to deal with profinite completions. And this is not for nothing. If you want to understand, if you want anything which contains the Galois group itself, the Galois group of Q itself, then you have to profinite complete, because the Galois group is a profinite group. So if you take the pro-unipotent completion, which in some sense, it's not really a quotient, but in some sense, the pro-nilpotent, it's the algebraization of a quotient of the profinite completion, then you get something which you get only a trace of the Galois group, which are called now Deligne-Hara algebras. But you will never manage to get the full Galois group. So why does he do that? Well, because he had just written papers about rational homotopy theory. So rational homotopy theory is precisely busy with these kind of things. So what Deligne did is let the domain shift from profinite to pro-unipotent profinite. So if you go to a pro-unipotent side of the theory, then first you give up the dream of which is expressed in the Esquisse program to capture the whole of the GAGA group, and also you confine yourself necessarily to the moduli stacks of genus 0, 1, and 2, because the Torelli groups are enormous. And if you go to higher genus, then this thing does exist. Sorry, this thing, the analog of this thing does exist for moduli stacks. There were actually the Torelli groups were slightly, I mean, not slightly, but they're very mysterious, but there was the first result by Hayne. But all in all, you're basically confined to genus 0 and 1. I could say that genus 2 is an extremely good provider of PhD thesis, because nobody wants to talk about hyperelliptic curves, because what you can do with hyperelliptic curves, usually you can do with elliptic curves. But okay, genus 2 is still possible because every curve of genus 2 is hyperelliptic. But genus 3 becomes essentially impossible. So here, but this is exactly where you divorce from topologies, geometers, and so on, because Teichmüller theory starts in genus 3. Teichmüller theory in genus 1 and in genus 0, 1, and 2 is sort of baby to Teichmüller theory. The real Teichmüller theory starts in genus 3. So once you've done that, in some sense, you have given up many of the very ambitious or maybe over-ambitious ideas which are contained in the Esquisse. But what you can do, and this is very ironical, is deal with motives. So what Deligne says, which is very ironical if you read Récolte et Semailles, what he says, I cannot deal with this because it's too complicated, but I can use Grothendieck's theory of motives. And this is where he invents what we now call mixed state motives. Actually, it does not construct the category of mixed state motives. It just gives the realization, and it says a motive is a coherent set of realizations, and the category was actually constructed by Mark Levin just a few years after. I mean, very little, like 1 or 2 or 3 years. Okay, so that's probably enough. I will list some more sources which are more indirect sources, and I'll speak a little bit about them. So these are the 4 direct sources of Grothendieck-Teichmüller theory. And what I'd like to stress again is that it is actually a very vast and very, at least in Grothendieck's mind, it's a very vast, and it contains, let's say, it touches many, many mathematical domains, and which some of them have been left aside, or maybe they exist. Oh, actually, I worked on them, but they're not considered very often. Again, one domain which we'll not even touch upon is deformation, modern deformation theory, including string topology, including other things which we won't talk about at all. So in the prehistory, I should mention, because this is really important too, Neukirch, maybe Neukirch Ikeda. I don't know if there is a first name in Japanese, and I don't know the first name of Ikeda. But Neukirch Ikeda, but okay, I just mention it because you need to know a little more about abelian geometry in order to talk about it in a sensible way. Let's say it's a prehistory of abelian geometry before abelian geometry. And somebody who is probably more surprising, that's a little bit of my own fantasy, is William Thurston. So actually Thurston has a famous work on diffeomorphism of surfaces around 1978. Just like everything with Thurston, he understood everything and he didn't write very much and it was not very well written, but he understood everything. And that work of Thurston on diffeomorphism of surfaces, in some sense, I think is very relevant. I try to explain it because in some sense, again, what Grothendieck in some sense would be after is the theory of profinite surfaces, profinite geometry. Usually what you call profinite, now we have profinite groups. They were invented by Krull in the 1930s, but profinite geometry is something which is much more, much vaster. And maybe if I have some time, I doubt it, maybe on Friday, I'll give a very, very, a very cursory glimpse of what it can be like with profinite complexes of curves and so on. So now, as an illustration, I would like to tell you about P1 minus 3 points, but in all, and it's not the second talk. So the second talk, I'll talk about the Galois action on the pi1 of P1 minus 3 points, which is basically descent enfant, but without descent enfant, just viewed from not from the sky. Well, from the sky in the sense that from above, from the universal cover. But here I'd like to talk about P1 minus 3 points from 3 different points of view, 4 different points of view, many different points of view. So there will be topology, complex geometry, no, hyperbolic geometry. This is an illustration of the fact complex, hyperbolic, complex, and arithmetic geometry. This is also a very important thing that what was striking to Grothendieck first is this, pi1. We're talking about pi1. And second, that there's like a self-rigidification. Like you start from topology, then you rigidify to hyperbolic geometry. Hyperbolic is the same as complex for surfaces, not in general, but for surfaces. And we stay with surfaces. He writes that he was giving a course in Montpellier to people to very ignorant. I mean, even first-year students, but also not very motivated first-year students. They were very motivated by Mai 68. And he says, okay, I'll come with my little surfaces and how do you call it? The thing you manipulate when you're a child. And I'll tell them about it. And that's how it all started. So it's about surfaces in the real sense. So curves in the curves for over the complex, say. So it's about surfaces. And so hyperbolic and complex will be the same. And then there is arithmetic geometry. So the thing which is striking is that this self-rigidification. So what about first topology? What can you say in topology? Well, topology, you can say it's fairly elementary in a way. So topology, you say that you have a sphere. So you have a sphere with 3 holes. Okay, so you usually write it this. I mean, you usually draw it this way. So Americans object to call it a pair of pants for reasons which are not mathematical. So you can call it a trinion, for instance, which is sometimes called pair of pants. Well, so this is a building block of surfaces, first of all. So that's easy. So the Euler characteristic is -1. So it's the building block of hyperbolic surfaces. So a hyperbolic surface, so a surface, well, here I try to introduce just notations and so on for the later conferences, in fact. So SGN will be surface of genus G and N, so which N something, which are called mark points, punctures, or simply holes, like here, depending on what kind of mathematics you're talking about. So it's so of course let's say minus the Euler characteristic of this is 2G minus 2 plus N, and it's hyperbolic if the surface, if the Euler characteristic is positive, is negative. So this thing is strictly positive. So you see that if G equals 0, N should be at least 3, and if G equals 1, it should be at least 1, and if G is strictly larger than 1, it could be anything. And if this is additive. So SDN. So this is additive. So sorry, this is additive when you cut. That's what I meant. So if you cut SDN into trinions, then you get. So how do you do it? You do it this way. Let's say I take S. I don't know, S21. This is S21. It's not very nice, but it's S21. So you cut it into trinions like this. And the number of trinions, is 3G minus 3 plus N. So this is not additive. Every time you cut a surface, this number decreases by 1. Even if you take the sum of the number of trinions in the various connected components, this decreases by 1. So this is a very important number, because not by chance, D equals DGN, so D equals DGN equals G minus 3 plus N, is also the dimension over C of the moduli stacks of these things. So MGN is the moduli stack of the moduli space of which classifies the surfaces. What? The number of loops. Oh, yeah, the number of number. Sorry. I meant the number of curves. Number of curves. The number of loops, if you want. Yeah. Of course, not the number of trinions. No. Of course, the number of trinions is 2G minus 2 plus N, and the number of curves is 3G minus 3 plus N. Sorry. No, of course. Okay, but that's, yeah. Well, that's more, okay, then we'll come back to this. This is important, and this is not by chance, because it has to do with Fenchel-Nielsen coordinates. Fenchel-Nielsen, which I don't know, I won't talk about it, or maybe I will, but I want to have time, really. But this is of course not by chance that the number of loop is equal to the dimension of the complex dimension. So the number, so functional Nielsen coordinates, these are real analytic coordinates on this, not complex analytic. So the number, so the real dimension of MGN is twice the number of loops. And this is completely, I mean, if you know a little more, it's completely obvious because any loop will give you a twist and a length. So any loop will give you two parameters, and the functional Nielsen coordinates are real analytic, and so you have the real dimension is twice that. But I don't think I'll have time to talk about it, but at least it's a good transition to hyperbolic geometry. So hyperbolic geometry, you can say a lot. And I'm very much indebted to Tiwari to telling me about these things. I'm going to say almost nothing because, well, but everything is written in, for instance, in a, how do you say in English, panorama et synthèse? It's an AMS series. We wrote it in French, but then it was translated by the AMS into a series which are, in French it's panorama et synthèse, but in English I don't remember, something series. I don't remember the title of the series. And we wrote a long introduction with Tiwari about this thing. What can I tell you? Just not too much because I don't have time, but yeah, if you have a surface which is hyperbolic, then you have only one metric on it of curvature -1. So you take your metric of curvature -1, and there are, what are the main, well, no, there are many things you can say, but one thing you can say is that a trinion is made, so equipped with a metric of curvature -1 is made of two hexagons with right angled hexagons. Two identical right angles hexagons. So how do you build this? Well, just this way. So you have one here. So you have no choice. I mean, now we have curvature -1, and you have two hexagons like this. And this is determined, they're determined by the lengths either of the sides of the opposite sides, so three lengths, this one, and this one, or, and well, let's do that because it's better, or this, and this. They are identical. So everywhere I don't write too much because everything is written somewhere. Now, maybe not what I said at the very beginning, which was very general. But here, of course, it's written and it's very much more. So here you have a hexagon. They're identical. So the other face is the exact other hexagon, which means here, this is equal to this. So if I give you this, and this, or if I give you this, I give you the length. Okay, and how do you reconstruct a surface? Like here, you take your trinions, and and they have to have, of course, the same length. Otherwise, it doesn't fit. They have to fit. You fit them, and then you have a twist. So the two parameters here are this length, or say the double, the length of the loop, plus the twist. I mean, here you draw another one. So this is the first way of building up surfaces. You have trinions, you glue them, so they have to have the same length, and you twist like this. So you have an angle. So on Teichmüller space, the angle can be any real number. On moduli space, it's modulo 2 pi. And you have the length. So these are the two parameters per loops. And this gives you the Fenchel-Nielsen coordinates, which are, again, I insist, not complex analytic, but real analytic. So you have here a length and a twist. And so that's exactly what you have per. So, and maybe I mentioned another extremely important phenomenon in algebraic, no, not algebraic, in hyperbolic geometry, which is the following. Suppose I have a copy of M0, P0, of a surface of genus 0 with 4 points. So here I have a geodesic. I have only one, because the number of I forgot to tell you that all these curves are geodesics in hyperbolic geometry. Hyperbolic geometry on a surface in any homotopy class, you have one and only one simple geodesic, and that's what you choose. So what happens if I squeeze this? So squeezing a geodesic, squeezing meaning just let the length of this geodesic, let's go to 0. Letting the length of a geodesic go to 0 is going to the boundary of the moduli stack. It's the same as going to the boundary of the moduli space. And what happens is that hyperbolically speaking, you have this. This becomes longer and longer. So you have a long, thin part of your until you get when it's 0, you get the cusp. Okay, you have two cusps. So what does it say? Now imagine you want to transverse geodesic, which would be like this. Now they cross, and the color lemma, say, maybe it's usually called the color lemma, it can be called anything. Say that there exists an absolute constant, absolute meaning it has nothing, it's independent of G, independent of N. Actually, I think it's log of 1 plus square root over 2. I'm not completely sure. Such that on any surface of curvature -1, so and mu, say, two curves of length strictly smaller than mu do not intersect. This is really important, and we will use it on Thursday for the two-level principle. This is one way of when Grothendieck, the way he puts the two-level principle without vindicating it, because you need other stuff. In particular, you need this, but you need more. So there is a constant such that if two curves are short enough, they do not intersect. That means if you go to the boundary of the moduli space which is exactly given by shortening curves, by collapsing curves, by creating nodes, then you will have you will be able to have definite decompositions, what we call maximal multi-curve or trillion decomposition of your surface. So let me stop here for hyperbolic, because complex and I won't say much, of course, about complex and arithmetic, but still. So now, so you see this object, this very simple object, is actually quite important. And I'll say more maybe in the second talk about how universal it is. But for the time being, let's go quickly to complex geometry. So what do you say in complex geometry? Complex geometry, so first, it is, I can't say it's a coincidence, but almost, that in dimension 2 or in complex dimension 1 is the same to choose a metric of curvature -1 and a complex structure. This is not true in higher dimensions. This is true because of the uniformization theorem. So the uniformization theorem is a big theorem. So it tells you that if you have a hyperbolic surface, then the analytic, how do you call it? Universal cover is nothing but the Poincare upper half plane. So that your surface, the Poincare upper half plane modulo Fuchsian group, and the Fuchsian group preserve both the -1 metric and the complex structure on the Poincare upper half plane on the Klein disk. And this is true only in dimension 1. I mean, it's rather the uniformization theorem, which is true in dimension 1 only. So this tells you that we're talking about the same thing. Now, here you have the fact that PGL2C acts, how do you call, thrice transitively. So you can bring 3 points to P1 to 0, 1 infinity. So this not too much of a problem. And then you have a big theorem, which tells you that there is only one complex structure on P1, which is also not at all obvious, which all in all tells you that the moduli space of the surfaces of M03 is 1 point. But I mean, people tend to take this as something sort of obvious, but it's not obvious at all. It uses the uniformization theorem, which is elementary and easy, and the fact that there's only one complex structure, which is not at all easy. So this is essentially what you can say. No, sorry, I take it back. This is what I am going to say, because otherwise they will go too far afield. And the last thing I would say is arithmetic geometry. And here I want to make a statement which I've never seen in print. By the way, this I think could be the theme of how do you call it? Maybe a master's degree or whatever. I mean, and which is to say that P1 minus 3 point. How do you P1 over Z? Well, I insist. P1 over Z minus 3 points is up to automorphism. The only hyperbolic, smooth, so everything counts, smooth, hyperbolic curve over Z. So here, this is an exercise. So you have to remember what smooth over Z means. So this is real Grothendieck, SGA, I don't know, 1, or AGA. Hyperbolic, which means the fibers over the prime numbers are hyperbolic, because here you have over, I would say, spec Z if you want. Spec Z is more correct. So over all the primes are hyperbolic, and actually there's a continuity of the Euler characteristic, and yeah, and that uses this is not trivial. It uses a result of Fontaine, which is not very difficult, which says that there is no smooth abelian variety over Z, over spec Z. So if you try something which has genus strictly larger than, I mean, it's not 0, strictly bigger than 0, then it has it will have the Jacobian. The Jacobian will be an abelian variety, and it will be smooth over Z, contradiction. So it has to be of genus 0, and if it's of genus 0, you will see very quickly that there is not much you can do, except putting a -1 here. But then you have the automorphism, which sends Z to -Z. And so I think this tells you that P1 minus 3 points is really, if you consider, I should say, Grothendieck-Teichmüller theory is over Q. Everything we do is over Q, which is the generic fiber. But you can go, if you go a little bit beyond and you go to Z, then you have this characterization of P1 minus 3 points. Okay, I'll stop here. And yes, and I thank you for your attention, possible maybe. So is there a T here? I mean that it's hyperbolic over any prime number. The fiber over a prime number is. Yes. The fiber over any prime number is hyperbolic. I'm not a specialist of that. I think this is. Maybe there's a global way over spec Z. I don't know. Frankly, I don't know. Here, I just mean, also there's a continuity of the Euler characteristic from one fiber to another. I mean, the Euler characteristic is the only thing which is the only invariant which is continuous from the for a smooth map along the fibers. So it's actually you need only one fiber, and you can take the fiber at infinity. So I think it's actually easy to define in this particular context. Maybe over any base, there is a more sophisticated definition. Sorry?
More elementary doubt.
Sorry,
No, I just want to know why do you need to choose right angles in that?
Oh, they come. That's the way they are. Everything is geodesic. This is a geodesic. This is a geodesic, and this is curvature -1, and this is not what you need the right angles. They are. That's what they are. You don't choose. You don't choose if you have two geodesic. Let's say if you have two well, in some sense it's very intuitive. If you have two geodesic and you want to join them by geodesic, if you think in terms of variational calculus, imagine that the angle has to be a right angle, because this is the shortest distance between these two things. So.
Any other questions?